So good morning students. In the previous video we had seen about the initial value theorem and final value theorem and the problems related to that. Now in this video we will be seeing the standard functions what we are going to use in your systems, in your circuits. So here your standard functions are nothing but your singularity functions there. So mainly we have three important singularity functions, that is one is your unit step, unit response, the unit impulse and unit uh, ramp function there. So here your unit step function is going to be denoted as u of t, delta function is going to be denoted as del of t, and ramp function is going to be denoted as r of t. So why these functions are going to be called as singularity functions is there doesn't going to be exist fine, they are not going to be finite or do not going to possess any finite derivatives everywhere there. So in this case we do not have a finite function for that, and they do not possess the first order derivatives or finite derivatives there. So that is why they are called as standard functions. First we will see your unit step function. The name itself tells it is your unit step. So from the base level it is going to move a one step level there. So that step level can be by different amplitudes. So if that amplitude is going to be a, then we multiply that function by a. If that amplitude is going to be 1, then we multiply that function by 1. Unit step is one step ahead. We are moving the signal from one step to another step there. So here we say that this is your unit step function. At t is equal to 0, my step function increases by a magnitude of a. So I can write your f of t is equivalent to your u of 0 for t less than 0. So we can see that your time period, for time period t less than 0 it is going to be 0, and for t greater than or equivalent to 0 my amplitude is going to go to a and it is going to be maintained at that constant value. So since it is going to be maintained at constant value from t is equal to 0 to greater than 0, greater than or equal to 0, we write it as f of t is equal to 0 for t less than 0 and a for t greater than or equivalent to 0 there. Next is we are going to see a shifted unit step function. Instead my waveform is going to start at 0 if my waveform is going to start at some other point, this point, or some other this point, we can say that it is a shifted unit step function there. So here we have taken the example of positive shift there. So here my waveform is shifted by a time period of a here. So that I can write my unit step function, instead of writing it as u of t, it has been shifted. My unit step function has been shifted by a value. So I can write it as u of t minus a. So this is called as your unit step function. So multiplied by a constant, that is nothing but here 1. So I can write my expression to be u of t minus a is equivalent to a 0 for t less than a. So for t less than a, my u of t minus a is going to be 0. And for t greater than or equivalent to a, it is going to be 1. So we write this as your unit step function, the shifted unit step function. So next function is your use of unit step function. So use of unit step function is going to be, I am going to have the amplitude to be 1. So here in this case we are going to have your f of t function. So generally you are going to have the function to be present between your first quadrant and your third quadrant there. So when I am going to use my unit step function, I want the network analysis, the unit step function will be available for t greater than or equivalent to 0. That means my step function should be available only in the first quadrant. It should not be available in the third quadrant. So here in this case we go for multiplying that function, your f of t. To get that function f of t, we multiply that function by your u of t. So we write this, your f of t is equal to a into u of t for t greater than or equal to 0, and it is going to be 0 for t less than 0 there. So here we are going to have, if the waveform is going to be shifted by a negative axis, my amplitude here is going to be 0 minus of minus a. That means that it is going in the negative direction, and the amplitude is going to be a, in the negative direction is minus a. Total amplitude is going to be minus a there. So I can write u of t is equivalent to, your f of t is equivalent to minus a into u of t for t greater than or equivalent to 0 and 0 for t less than 0 there. So unit step function is, use of unit step function is, we are multiplying this f of t function is nothing but we are going to multiply any amplitude by u of t. Why we are multiplying by u of t is, I want in network analysis the signals are going to be analyzed only in the first quadrant and not in the third quadrant. To have my signal in the first quadrant, I am multiplying the amplitude with your unit step function. That is the purpose of unit step function there. Next is the gate function. Here the gate function can be constructed from u of t. So here it can be, it is a rectangular pulse which is going to start at t tau is equivalent to t is equivalent to tau and ends at t is equivalent to t plus tau. So like an on off switch, I can use this gate function there. So how I am going to write the waveform is, see first in this case I am going to split the waveform here. So if I split the waveform, so if I am going to split the waveform, first the waveform is going to be like this. So my waveform is going to start at tau point. So 0, it is going to start at this point there. So in this case, my amplitude is going to be here 1. This is going to be your, I can take this to be your f1 of t. Okay, whatever is this one you have followed, you can use it there. So here in this case, I'll write it as my unit step function, instead of starting at 0, it has been started at tau there. So I can write the unit step function as u of t minus tau. Okay, so that is your unit step function. That is the starting function there. Next is at t minus tau. So at this point, tau plus t, I want my waveform to be shifted. That is, I want my waveform to come down to 0 there. So for my waveform to come down to 0, the total amplitude here is going to be your 1. 0 to 1, the total amplitude is going to be 1. So but it is going in the negative direction. So negative direction means it is going to be minus u of t general by how much the waveform is shifted, it is t plus tau. So here in this case we can write it as tau plus t. So tau plus t. So if I am going to combine it, you are going to have, so this, I want only these functions. So it is the difference between these two functions. So u of t minus tau minus of u of t minus tau plus t. So that is what we have written here. Your gate function can be expressed as u of t minus tau minus u of t minus tau minus t. So the unit step function, so suppose for example your unit step function is going to be shifted in the negative direction, minus a. Then in that case I can write my u of t plus a as the input there. So the waveform is going to be shifted to the left side. So left side means it is u of t minus of minus a. That means u of t plus a is equivalent to 0 for t less than minus a and 1 for t greater than minus a. So for lesser than minus a, this is going to be 0 there, and for t greater than minus a, your t is going to be greater than that is, it should, your amplitude is going to be 1. So next function is your impulse delta function or impulse function there. So impulse delta function is, we are going to have your time period t and the delta function is going to have an amplitude 0 there. That is your amplitude 1. So how I can write is del of t is equivalent to 0 where t is not equivalent to 0. So here where in this case, this t in this case and all, your t is not equivalent to 0. It is going to have some values there. For all these values, this side or this side, I don't have any amplitude there. Only at t is equivalent to 0, I have an amplitude to be 1. So we say that the area under the pulse is going to be unity there. So now how I am going to take is, first I am going to take the first function there. So here in this case, your first function is going to be your t1 function. So in t1 function, the length is going to be t1 and the height is going to be, that is your breadth is going to be 1 by t1 there. So if I multiply for area, t1 into 1 by t1, it is going to be just 1. So we write A1 is nothing but the width into amplitude. Width is nothing but A1 into, here in this case, T1 into amplitude is 1 by T1. So we write it as 1. Next is A2. A2 is nothing but similarly it is T2 into 1 by T2, where T2 is going to be less than your T1. Next is A3. So A3 is nothing but T3 into 1 by T3. But T3 is lesser than your T2 and less than your T1. So we say that your del of T, we can define it as your del of T is equal to limit T tends to 0 f of T here. So your f of T is nothing but the area of the function. So A T into 1 by T. So that gets cancelled, and finally my area is going to be just 1. So the unit impulse function, it can also be obtained using your step functions. So we can use your step functions to obtain your unit impulse function, and it is going to be a limiting case for a rectangular pulse. So this rectangular pulse can be obtained by subtracting two step functions there. So your f of t is equivalent to u of t, that is the first one. Here it is your u of t, and minus of u of t minus t tau. So del of t is equal to limit t tends to 0, 1 by t into u of t minus u of t minus u of t minus t. That is your impulse function there. So next is your delayed unit impulse function. So delayed unit impulse function is, instead of at t is equal to 0, my waveform is going to be shifted by a value of a, the time period of a. It's going to have an amplitude 1. So I can write f of t is equal to del of t minus a. So the properties of your shifting impulse function is shifting property. So integral minus infinity to infinity f of t into del of t minus capital T into dt, that is equal to f of t, where del of t minus t is a delayed impulse function there. Shifting property is, by how much is the impulse function shifted, that is going to be the Laplace transform of that particular function, your f of t. Next is replication property. So replication property is the convolution of any function with an impulse function results into an original function. So I can write it as integral minus infinity to infinity f of t, f of tau into del of t minus tau into d tau. Next is your ramp function. So ramp function is, you are going to have a straight line there. The straight line is going to have a slope. So here wherever you are going to have a ramp function, a slope line, when you are going to perform the operation on that straight line, it will be surely having a ramp, and with that ramp, with that slope, we will be writing the equation. So f of t is equal to a into t for t greater than or equivalent to 0. So we call a is going to be called as the amplitude and the magnitude of the ramp function. So here next is unit ramp function. So unit ramp function means the both your width as well as the breadth is going to be just 1. So we write r of t is equal to t for t greater than or equal to 0. It is going to be 0 for t less than 0 there. So the ramp functions with unity slope is going to have magnitudes of 1 always. So it is going to be called as unit ramp function. So r of t is equivalent to t into u of t for t greater than or equivalent to 0. So it is going to be 0 for t less than 0. So the ramp of magnitude a, it can be expressed in terms of unit step function. So f of t is equivalent to a into t into u of t, where u of t is nothing but a unit response function and a is the slope of the ramp function there. Shifted unit ramp function. So the ramp function is going to be shifted by n value a, so it is going to have a slope of 1. So I can write my f of t is equivalent to t minus a for t greater than or equivalent to a, and 0 for t less than a. So f of t is equivalent to t minus a into u of t minus a, where u of t minus a is nothing but a unit step function delayed by or delayed at t is equivalent to a. So the shifted ramp function, which is going to have a magnitude of a, can be expressed as, so suppose for example it is shifted by t minus, that is a means we write it as f of t is equal to a into t minus a into u of t minus a for t greater than or equal to a. It is equal to 0 for t less than a. So the delayed unit ramp function can also be denoted as r of t minus a. So here we write your slope is going to have a negative slope. So negative slope means your f of t is going to be minus a into t, u of t. So f of t is equal to shifted by a means f of t is equal to minus a into t minus of a into u of t minus a, where t into u of t is going to be a unit ramp function and t minus a into u of t minus a is going to be the shifted unit ramp function. So addition of two ramp functions. So consider two ramp functions having equal at opposite slopes. So a and minus a. So when I am going to add these two ramp functions, finally a minus a is going to be 0. It is going to be maintained constant. So we write f1 of 2 plus f2 of 2 t. So your f of t can be written as f1 of t plus f2 of t is equal to 0. So an addition of your a minus a is going to be 0, and that is nothing but a constant for t greater than 0. Next is, here in this case, after addition of two ramps, we are going to add these two ramps. The resulting function is going to be just a constant there. So here we are going to have the addition of this is your plus a, this is going to be your minus a. If I add these two, I will be getting a constant, that is nothing but f1 of t plus f2 of t. So we say that after addition of two ramps, the resulting function is going to be a constant 1, where it is going to be equivalent to 1 for all t greater than 1. So here it is going to be 1. For all t greater than 1, this is going to be a constant 1. So here this is going to be used for the problems there. This concept will be used for the problems. Thank you.